In Module 3.3, we investigate univariate random number generation and its role in different financial applications. We will circle back to multivariate random number generation when we get to dynamic risk measures later on in the book. But in this particular module, we're basically just introduce the concept of random number generation. We'll illustrate graphically some uniform distributions, uniform numeric and integer. We'll introduce the normal distribution as well as a Bernoulli distribution that's useful in credit analysis. A uniform distribution with the range 0 to 1. What's illustrated here on the left-hand side is a random sample of a uniform distribution with a mean of 0.5 and a range of 0 to 1. And what we see is that it is quite random and it's very useful when you're trying to map out some sort of random variable. And the random sample, the different outcomes clearly oscillate. The PDF basically in theory should be 1.0, but with a random sample we get noise around that value. If we take a uniform integer from say minus 100 to plus 100, the distribution looks very similar. And again, the PDF varies quite a bit depending on the different frequency of outcomes. Real numbers as opposed to integers looks nearly identical. The difference here is that the numbers are stored with a high level of precision as opposed to just integers themselves. The normal distribution, if you'll notice, this looks significantly different in how it maps out, in that we have more observations around 0. The normal distribution with mean 0, standard deviation 1, has the familiar bell-shaped curve. The histogram produced by this small sample doesn't map exactly to the PDF, and we would not expect it to do so. This is a sample of 100. The population mean is 0. The sample mean is not 0, and so we don't. When you have a random sample, it doesn't give you the precise population parameters back, but it does tend to move closer as you increase the number of observations. We can change the mean and standard deviation if we assume, say, some stock has a rate of return of 10%, a standard deviation of 30%. We could run a simulation with an adjustment for the mean and standard deviation, and we see that the numbers oscillate around 10 with standard deviation 30. Again, we get the familiar bell-shaped curve, but because this is a sample of only 100, we still have an enormous amount of sample error in our estimates. The final distribution that we examine here is a Bernoulli distribution, and basically it's a binary 0-1 depending on whether or not an outcome was observed. And so we're looking at the desired likelihood of 25%. So 25% of the time we observe, we'll pull the number 1, say, and otherwise it's 0. Bernoulli distribution is particularly helpful in understanding credit risk and related issues. So in summary, we just introduced the random number generation. We illustrated them graphically. And in the source code that we'll turn to now, we'll look at some large sample properties. We now take a look at the source code that accompanies Module 3.3, Univariate Random Number Generator. If you'll notice in this particular folder, there's only 2 pieces of R code. One is the simply testing various univariate random numbers and generating some plots. The other is a layout that helps you understand large sample properties And the way we launch RStudio, remember, is just double click on the RPROJ. And we have these two. If you'll look down here in the files, there's only these 3 files. The 2 test programs are already loaded up because this is how I left it. And so let's quickly work our way through the univariate random number generating test. Again, the green is simply comments. This is taking out the trash, setting up some preliminary packages. Remember, these packages, if we look at the stats, generally stats is always loaded, but just to be sure, we could load the stats if we wanted to, and then make sure it's installed, which it is already. It's not a problem. And so if we set some input parameters, a number of observations, say 1, upper bound, lower bound, the sample draw, this is a random number. And so if you'll notice, you can highlight line 24 and just run it over and over, focus your attention over here. And what you see is you have a random number somewhere between 0 and 1. If we wanted to know the quantile value at 75, we could, if we set the quantile value at 0.75, then the PDF is 1.0. Because that's it's a constant uniform distribution. The CDF is going to be 0.75, and then the quantile function is going to be 0.75 also. If we wanted to set how many digits and the kind of numbers we want to see, if I set the digits to 4, the graphs are less cluttered. So let's start with the number of observations being 100. We set the X and Y variables. We run the random number generator. So the X and Y, if you'll notice, X is an integer from 1 to 100. Y is the random draws. And so again, if we highlight line 42, if you'll focus your attention over here, run it multiple times, and you see that it generates different samples of 100. We could calculate the sample mean, which should average around 0.5. So if we highlight both of these lines and just run it over and over, we see that that number oscillates around 0.5. We could generate some graphs if we wanted to of this particular result and run just this section of code, and it generates the graph down here. Generally, I like when producing graphs, if you make them a little bit bigger, it looks better. When you're trying to understand different properties. You can highlight the entire set and run it over and over, and what you observe is that the histogram changes depending on the draw. If we increase this to 10,000, then we'd expect that histogram to be more stable around 1.0, and so we run it at 10,000, and that's in fact what we find. So the larger the sample size, the lower the sample error that occurs. And so if we do a uniform integer, we can look at how that works between minus 100 and plus 100. The number of integers is going to be the upper bound minus lower bound plus 1 because of the 0. And then the machine error, not machine error, but this lets you know the maximum size of an integer. It depends on the particular machine that you're running on. And so if you'll notice, we take a sample of the integers. And so in this case, Y is a random, it's a random sample that changes depending on the particular draw. Again, we could graph this result. If you'll notice in the graphs, we have the plot itself, and then we could add a histogram, or I'm sorry, we could look at a separate file of the histogram along with what the PDF should be in the limit. And so again, we could highlight this whole range, run this over and over, and we get different results for each run. The beauty of random number generation is that it gives you different outcomes than what you actually see in history. And so when we get to dynamic risk measures, Monte Carlo simulation is very useful in the sense that we get observations that have not been observed in the past. And history has taught me that those things which have never happened in history do in fact happen. So example 3 is just simply a uniform random number generation with a different limits. The standard normal is simply running this R norm. And again, we could just run this program to look at the different samples that occur. And again, if we increase the sample size to say 100,000, now back in my youth, that would have taken forever to run. But on the laptop that I'm doing this training through, it's incredibly fast to do that many simulations. And what you notice is that every time I run it, if you look at this mean, it'll change, but it runs very, very fast. And so it's just incredible. The computer power that you have available to you to do quantitative financial analysis. We can obviously change the mean and standard deviation if we wanted to. And the mean and standard deviations of the sample will shift. And the final one, this is an interesting exploration in credit risk or other kinds of binary events. You can do a sort of a Bernoulli distribution where you either have default or you don't have default or something along those lines. And so this particular code, I'd encourage you to spend time with it just to get familiar with generating random numbers. The other piece of code that is available is looking at different the effects of different sample sizes. And so let's just look at the normal distribution, which I think is, let's see, uniform likelihoods. Here we go. The normal distribution. This sets a function that computes the different parameters of the sample mean versus the population mean. If you'll notice, if we increase this to, again, to 100,000, with only 100 observations, you get a big difference between the sample mean. But if you do 100,000 observations, then, oops, I had to reload the function. And so what you observe now is the mean is very close. The sample mean is very close to the population mean, and the sample standard deviation is very close to the population standard deviation. And this still ran incredibly fast. And so the computer power that you have access to is phenomenal. Thus, the ability to generate random numbers is extremely useful in a wide array of different applications in quantitative finance. And this source code is a great place to start to understand exactly how to use random number generation.